Okay, so on this one here, we have a 75 kilogram sprinter. So they gave us the mass. Okay, and they gave us the force, 225 newtons. Okay, over the last 10 meters of the race, okay, they increased their speed from 14 meters per second to an unknown speed. Okay, what is their maximum speed? All right, so is work being done? Okay, what kind of energy is it changing? Kinetic. All right, so work is a change in kinetic energy, which is going to mean force times distance, since I have both of those numbers, equals EK final minus EK initial. Now what I'm looking for is final speed, which would be part of which one of those terms? EK final. All right, so I want to get EK final by itself before I put the 1/2 mv squareds in. What do I have to do with EK initial? Add it to the other side, right? Do the opposite. Okay, so the change in energy, force times distance, plus the initial kinetic energy should equal my final kinetic energy if I'm talking that through logically. Okay, so we would have then force times distance plus 1/2 mv initial squared, I have all of those numbers, equals 1/2 mv final squared. How do I get v final by itself? Divide both sides by 1/2 of m, and then square root. Okay, so I will have then the square root of 225 times 10, so force times distance, plus 1/2 times 75 times 14 squared, divided by 1/2 times 75, all square rooted. If you're not careful about punching them in your calculator, though, then it might not.
Oh, that's why you ran 1,200 meters per second.
Yeah. Seems a little fast.
Yeah, I didn't have time to redo it.
In as much as that's almost Mach 4.
I didn't have time to redo it.
Okay, so guys, to avoid the calculation errors, or at least minimize the chances of making them, don't try and enter this into your calculator in one go. Okay, I would go 225 times 10 and hit enter. All right, now I've got that first part done. Then I'm going to add that to 0.5 times 75 times 14 squared. Now I've got the top done. Okay, divide that by 0.5 times 75 in brackets. Now I've got what's underneath the radical. Okay, now I can just square root that. All right, 16 meters per second, which is a much more reasonable number than Mach 4. Okay. 16 meters per second. Okay, ringing a bell? Okay. Okay, I was telling you about this one on Friday, but we never got to it, okay? One where you use a bow and arrow, but you shoot it straight up in the air, which, if it's a very calm day, is not a good idea. Okay, that whole what comes up must come down thing, you know, so get out of the way. Okay, but give this one a try. Let's see if we can find out what height it would reach if it was fired from the ground. Okay, from the ground means your initial height is what? 0. Right. Okay. Okay, so on this one here, guys, okay, we have the mass of the arrow, 0.09 kilograms. Okay. We're looking for its final height. We know it's fired from the ground. Okay, it uses 300 newtons worth of force. Okay, while being pulled back 0.75 meters. All right, so there's our givens. Is work being done? What kind of energy is it changing? Potential. Okay, actually two different kinds of potential. The elastic potential of the bow, which we're not concerned with, okay, and the gravitational potential of the arrow, which we are concerned with. All right, so we got force times distance equals final potential minus initial potential, except this one's a little easier because our initial potential is what? 0. Do you have a question?
Why are those marks on like a rate response on multiple marks if I didn't have a little change sign in front of energy potential, can I just put work equals energy potential?
No, not true.
But would I have to have a triangle in front of my?
Yes.
Okay.
Work is a change in energy, okay? The only time it would equal the potential energy is like in a situation like this one where it just so happens that the final potential energy and the work are equal. So if you had EP final, that would be true, but if you just had EP, they're not the same. Okay, so force times distance equals m times g times h final. We're looking for h final, so all we have to do is divide both sides by m times g. So we have 300 times 0.75 divided by 0.09 times 9.81. Oh, need brackets there. All right, so it's going to reach a final height of to 2 significant digits. 2.5 times 10 to the 2 meters.
Why is it only 2 on that one? I don't. Which one has it?
This is not a measured value. Yeah, a leading 0 is not measured because there's nothing to measure there. Yeah. Actually, sorry, this would be 3. We'd have 1 significant digit because of the 0.09. Now, I'm not going to test significant digits. I'm not going to test them on the test. Okay? I'm just going over them with you because, well, you guys are AP and you can handle it. Okay? It's like one of the first things you're going to learn in any 20-level course that you take. Chem 20, Physics 20 especially. Yeah. All right.
Will we have to bio?
What's that?
Will we have to bio?
No.
Yeah.
Really?
You just don't do as much math in bio, so they probably don't cover it right away. Right, that one's an easy one. That'll take you no time at all.
I'm really working hard on it.
Okay, so on this one here, they tell us the amount of work. Does that make our life easier? Yeah, because then we don't have to worry about force times distance. They already told us what that equals. So we have 6,000 joules worth of work. We have a 500 kilogram mass, and we are moving from a height of 14 meters to the top of a building whose height is unknown. Okay? All right, so we already know work is being done because they told us outright, here's the amount of work. What kind of energy is it changing? Potential. There's no mention of change in speed here. All right, so delta EP, so that means work equals m times g times hf minus m times g times hi, or EP final minus EP initial. Now, I need to get hf by itself, so what do I do with the mghi? Add it to the other side. Okay, so work plus m times g times h initial equals m times g times h final. What do I do with the m and the g? Divide them over. Okay, now I'm calculating HF. So 6,000 joules plus 500 times 9.81 times 14 divided by 500 times 9.81. Okay, so 6,000 plus 500 times 9.81 times 14, and it gives me that number. Divide that by 500 times 9.81. Okay, gives us 15.2 meters. That's a small floor. Since we started at 14 meters and only went to 15.2 meters, we didn't go very far. That would be a very low ceiling on that floor. Okay, if we only went up 1.2 meters. Okay, so the actual height of the building to 2 significant digits would be 15 meters.
Wouldn't it be 29 meters if you started from 14?
Nope, I was calculating the final height, right? I already subtracted the energy from the 14. Okay, does that make sense? I didn't calculate the change in height. I calculated the final height. Okay, it's a poorly made question. Probably because I just picked the numbers out of my head really quickly and they messed up. Maybe I should change it right now while I'm thinking about it.
Yeah, make it like 60,000.
Fixed. Now it'll be bigger.
I have to do that all over again.
No, you're not. Okay, last one we're gonna do. Okay, this one has to do with, okay, an inclined plane. Okay, you're rolling a ball up a ramp, kind of like Sisyphus, who, was sentenced to roll a rock uphill for all eternity. Okay, Greek mythology. Okay, so you're rolling it up at a constant speed, which means you're not changing the what? Yeah, the speed and the kinetic energy. Okay, if you're rolling it up a hill, you are changing the potential energy because it's getting higher. Okay, but by telling you it's moving at a constant speed, they're telling you you are not changing its kinetic energy. All right, give you a little bit of time on that one. So, the whole purpose of an inclined plane we talked about last week, right? It makes work easier. It doesn't make less work. Okay? It doesn't matter whether I lift this thing 8.2 meters to the top or whether I roll it up the ramp. I'm going to do the same amount of work because I'm going to change the mechanical energy of the ball by the same amount regardless of how I get it there. Okay? So our givens in this question are that we know the mass, 1.2 kilograms. Okay? And we know that it's going to be rolled over a 22-meter distance. How do I know that 22 meters is the distance?
Going up the ramp.
That's the direction I'm going, exactly. I'm exerting the force up the ramp. It didn't say I lifted it, okay? It said I rolled it up the ramp. So I'm exerting force along this part of the diagram, okay? Now, my initial height is going to be what? Right, and my final height is going to be 8.2 meters. All right, all I'm looking for is the force used to push it up the ramp. Okay, so work is a change in what kind of energy for this one? Potential, because it specifically said, as we said before, we are not changing the speed, therefore we are not changing the kinetic energy of the ball. Okay, so force times distance is going to equal m times g times h final minus m times g times h initial, which in this question is 0 anyway, because we start at the bottom of the ramp where the height would be 0. All right, so all I have to do to find the force is divide by distance. I want to leave force over here by itself. Okay, so I'm going to divide both sides by distance. Okay, force is going to equal 1.2 times 9.81 times 8.2 meters, okay, divided by 22 meters. All right, so 1.2 times, not divided, times 9.81 times 8.2. All right, divide that by 22. So I would have to use 4.4 newtons worth of force. Okay, now compare that to this, guys. If I wanted to lift it, I'd have to use that much force. Okay.
But over a shorter distance.
Over a shorter distance, but if I'm not strong enough to exert that much force, okay, then the only way for me to get this to the top of the thing is to move it up the ramp.
I really hope you're strong enough to lift all.
Me too. That's a pretty pathetic amount of force. You guys exerted that much force on the springs in our rubber band lab the other day. Okay, so yeah, I would hope I'd be able to do that. All right, that making sense to everybody? Don't expect anything different on your unit exam in terms of work energy theorem. Okay, it's going to be just like those ones, okay, that we just did. All right. So, can I get you guys to find, I believe it's lesson 13 on the law of conservation of mechanical energy, please. Okay, so what we're going to talk about now is essentially the last concept. We do still have to talk about efficiency, but it's pretty minor. What we need to talk about now is the law of conservation of mechanical energy. Now, the law of conservation of mechanical energy says that energy cannot be created and it cannot be destroyed. Okay? It can be transferred, it can be converted into other forms, okay? But it's always going to be around. Now, what that means is that if I throw something up in the air and have it come back to my hand, once it leaves my hand, through its entire flight, it has the same amount of energy. Because energy can't be created and it can't be destroyed. So once it leaves my hand, where I'd be doing work, right? I'd be lifting it, pushing on it. Okay? Once it leaves my hand, whatever amount of work I did, that's the amount of energy that that thing has until the moment I catch it and do work again in stopping it. How is that possible?
Because it's just stored in different forms of energy.
Exactly. It gets converted into different forms of energy as it flies up and down. Okay? When it first leaves my hand is when it's moving the fastest. Almost all of its energy at that point would be kinetic. As it goes higher, what happens to its speed? It slows down. Okay? But it's not losing energy. It's converting that kinetic energy into potential energy. When it's at its highest point, it's not moving at all. It has no kinetic energy at its highest point. All of its energy is now potential. And then it'll convert that potential back into kinetic as it falls back towards my hand and accelerates. Who is this who keeps calling me? It's annoying. Okay. Does that sort of make sense? Okay. So what we're saying is that energy is always going to be there. Okay. It's just going to be converted from one form to another. Okay. So what we learned on the very first day of this unit was that mechanical energy is the sum of an object's kinetic and potential energies. Okay? And the law of conservation of energy says that mechanical energy can't be created and it can't be destroyed. And we just said that through the entire flight of an object up and back down, its mechanical energy doesn't change. So that means then that in any perfect energy conversion, the initial energy and the final energy are equal. Okay? Now, this is very different from this. Okay? In a work energy theorem question, we're making the energy change because we're adding energy to the system or we're taking it away. Okay? Doesn't mean we're destroying it or creating it. We're just taking it from somewhere else and bringing it to the system by exerting a force through a distance. Okay? But in this case, we are not talking about any work being done. Right? We said once the object leaves my hand where I was doing the work, okay, now there's nothing doing any work on it. It just goes up and comes back down. Gravity is the only force present and it works equally in both directions. Okay? Everybody all right with that? Okay. So if mechanical energy equals kinetic plus potential, then what's really going on here is this. The initial mechanical energy equals the final mechanical energy, and mechanical energy is the sum of an object's kinetic and potential energies. So all I'm doing is writing the same thing, I'm just expanding it out here. So if this situation was back to me throwing that thing up in the air, okay, and this was the initial point where it just left my hand, all of its energy would be in what form? Kinetic, assuming I was at ground level, right? We'll simplify a little bit. And then when it's at its highest point, all of its energy would be potential. So would I be able to figure out how fast I threw it if I knew how high it went?
Yep.
Yeah, because the amount of energy it had at that point is the same as the amount of energy it had when I threw it. Okay, and that's the kind of thing you're going to be asked to find with a conservation of energy problem. Algebraically, they look a lot like the work energy theorem problems. There's a lot of moving things around and a lot of algebra to do. Okay, but in the end, they're also very patterned, just like the work energy theorem problems. Okay, the pattern is just slightly different. Okay, so for this first question here, okay, if I know the mass of this baseball and it's thrown in a straight line through the air, 2.5 meters above the surface of the earth at 20 meters per second, could I find its total mechanical energy? Yeah, okay, I could, because I know the mechanical energy is the sum of that ball's kinetic energy and potential energy. Okay, they told me the mass of the ball, they told me the height of the ball, and they told me the speed of the ball. So I got all the things that are part of this equation. Okay, everyone all right with that idea? So all I would have to do then is plug in my numbers, and I would know the total mechanical energy of the ball. So 1/2 times 0.3 times 20 squared gets me the kinetic energy of the ball, 60 joules. Okay, and because it's still 2.5 meters above the ground, okay, it still has some potential energy. Okay, 0.3 times 9.81 times 2.5 gives me 7.36 joules, right? For a total of 67.4 joules of mechanical energy. Is that a very hard calculation? It's basically just number plugging. Okay? Now, that ball is not going to travel in a straight line, is it? What's going to happen to it?
It's gonna drop.
Right, it's going to arc down to the ground like that. How much energy will it have right here the instant it hits the ground? Okay, what about the instant before it hits the ground?
67.4 joules.
Yeah, so how much does it have the instant it hits the ground before it starts to slow down? Like it just touches the ground? 67.4 joules. Law of conservation of energy says that the amount of energy that thing has at any point is not going to change if there's no work being done. Okay, so once that ball is thrown, it's got 67.4 joules worth of energy, and that number will not change. Okay, now when it hits the ground, yes, then that number will change because the ground will do work on the ball, it'll lose some energy, okay, and it'll slow down. Okay, everybody all right with that? Now, as this happens, as the ball arcs down towards the ground, what's going to happen to its potential energy?
Increase.
Decrease. And what's going to happen to its kinetic energy?
Increase.
Increase. Okay, that's how this number stays the same. Okay, an object's potential and kinetic energies just keep switching into each other. Right? It's what makes a roller coaster go. Okay, so most conventional roller coasters, you get towed up to the top of the first hill and then just released. Okay, your mechanical energy, okay, that is given to you by all the work done in towing the roller coaster to the top of the first hill is all that gets you through the rest of the coaster. Okay, it gets converted into kinetic and then back into potential and then into kinetic and then back into potential, okay, and so on and so on. Now, in the real world, does a roller coaster slow down as it goes along the track?
Yep.
Yes, because of friction. If I had a perfectly frictionless roller coaster,
Then the roller coaster wouldn't hold on to the things very well.
you're right.
And it wouldn't be able to get towed to the top very well.
Well, you could have a rope on it. You could tow it very easily to the top because there'd
But
be no
that rope
friction.
doesn't have friction to
Well, I
hold
just
on
put
to
the
the rope
motor,
to pull.
I put the motor somewhere else where it's anchored.
But what's the motor gonna hold on to? The frictionless rope?
No, I'm gonna tie it to the
How
front
can
of
you
the
tie a
coaster.
knot if it doesn't have
It said the
friction?
track is frictionless. Okay, does that sort of make sense though? Okay, so going up and down, all we're doing is converting kinetic into potential. Okay, that number, that total mechanical energy stays the same, which is why we can say this. Okay, now, The qualifier to that is that it does have to be a situation that is either an isolated system, okay, we talked about that the first day, okay, one that cannot exchange matter or energy with its surroundings, so it's perfect, okay, or it's frictionless or something else like that, that implies no energy is going to be lost because no work is going to be done, okay? All right, I would like you guys to try those 3 questions there. All they're asking you about is this formula. Okay, give you a few minutes on those. So on number 9, okay, they tell us the mass of the athlete, 55 kilograms. Okay, they tell us that they are attempting to clear the bar. At the top of the leap, the athlete has a total mechanical energy of 3,000 joules. Okay, and they are moving at 8.33 meters per second. Okay. Calculate the gravitational potential energy of the athlete. Okay, so mechanical energy, which I know because the question told it to me, is the sum of an object's potential energy and kinetic energy. So if I want to solve for potential energy, what do I have to do with kinetic? Subtract it over to the other side. Okay, so mechanical energy minus kinetic energy equals potential energy. All right, so if I expand that out a little bit further, okay, I'm going to have this 3,000 joules minus 1/2 times 55 kilograms times 8.33 squared equals EP. Everybody all right with that? Okay, so if I punch that in, I should get 10,091, right? So 3,000 minus, sorry, 1,091, not 10,000. 0.5 times 55 times 8.33 squared. Okay, 1,091 joules. We actually only have 3 sig digs there, so it would be 1.09 times 10 to the 3 joules. Okay, so that calculates the potential energy. Could I now calculate how high above the ground they are? Okay, if I know that this number here equals potential energy, is it safe for me to say this as well? It is, because I'm saying exactly the same thing I said over there. The potential energy is 1,091 joules. So if I wanted to calculate the height of the bar this person's trying to jump over, all I would have to do is divide mass times gravity over to the other side. Okay, so if I did that, purple, weird. Whoops, I didn't want to remove anything from Chrome, stupid. Okay. Okay, so I would divide, so I'm trying to get this, my calculator, okay, and divide that by 55 times 9.81, enclosed in brackets. Okay, so 2.02 meters, which I can tell you is an impressive high jump. Okay, I coached high school track and field for over 20 years. I can count on one hand the number of times I saw somebody go over 2 meters. Okay, it's an impressive jump. Right. So, questions on number 9. Okay, how many people have done 10? Okay, I'm going to give you a couple minutes. 10 is very similar. Here's what I want you to do on number 10. Do what it says first, calculate the kinetic energy, and then after you calculate the kinetic energy, calculate for me how fast the hammer is moving. Okay, both of those answers are there in red, 899 and 30 meters per second. Okay, so on number 10, we know the mass of the hammer, 2.00 kilograms. Okay, and we know that the hammer is 50 meters above the ground. Okay, and at that point, it has a total mechanical energy of 1,880 joules. Okay, we're looking for the kinetic energy of the hammer. So mechanical energy equals potential plus kinetic. Okay, how do I get kinetic by itself? Subtract potential over to the other side. Okay, so mechanical minus potential equals kinetic. Okay, so that's going to be 1,880 joules minus, 2 kilograms times 9.81 times 50 meters. Okay, that'll equal my kinetic energy. So 1,880 minus 2 times 9.81 times 50. All right, so 899 joules worth of kinetic energy. All right, now, second part of that, I said calculate the speed the hammer is moving at. So if EK equals 899 joules, then 899 joules equals 1/2 mv squared. And I know the mass of the hammer, okay? So all I have to do is divide both sides by half of m, okay? So by 1/2 times 2, what's 1/2 times 2?
1.
So I really just need to take the square root of 899, yes? It would come out to 29.9 something, which rounds to 30 meters per second. Okay, everybody all right with that? What we're going to be moving to, or moving towards here over the next few days, is being able to solve problems like this, but that have both sides. Okay, an initial energy and a final energy, where the energy is equal, okay, and moving things around to isolate. It's just algebra, okay? It's not going to be too terrible hard. You guys will be able to handle it, no problem. Now, couple of reminders for this week. Tomorrow, you still have a quiz, but it's a work energy theorem quiz. Okay, very much like the problems we did today at the beginning of class. On Wednesday or Thursday, I can't remember now which one it is, we're going to do a lab on conversions of energy. Okay, we will probably do efficiency on Friday, unit exam review a week from today. Okay, and then your unit exam is the 20th. Okay, so it's coming right up. Also remember, okay, that your lab report for the work lab we did last week is due on Wednesday. Make sure that you have it done for Wednesday, 8:30 a.m. in Google Classroom.